know whether it's the right moment to announce that this is the last one this year, because next Monday we have the meeting in Impact and one talk attached to it, and the week after is too close. Yeah, and the week after. Tuesday? Well, I speak about Monday. If I'm sure the week after there is no seminar. So welcome for the last seminar this calendar year. And since it is the exceptional occasion, I think we also have the chance to listen to an exceptional talk, which will introduce the results of a project for which the team was awarded Stephen Crowell Award by Clarin. So we can celebrate this award at the same time. As far as I know, the team was much larger, but that's what Martin will tell us. But for this talk, it's represented by 3 of the members of the team. So, Martin, that's your turn.
Thank you. So, good afternoon, everyone. I'm going to present a machine translator, which we in the end called Charles Translator. And the team was, yes, much bigger, and not only from ÚFAL, but we are the 3 people who focus mostly on the main MT training. So first, I will give you an introduction about the history already more than half a year of Charles Translator. Then Jindřich Helcl will give you an introduction to how never MT works in general, like very introductory. And Jindřich Libovický in the third part will talk about more detailed view how or the issues we are solving in Charles Translator. So how it all started. So exactly on March the 1st, this is the verbatim copy of email by Jindřich Libovický. Shouldn't we build a Czech-Ukrainian translator and put it on Lindat? And he already noticed that the quality of Google Translate is not satisfactory. And then this was confirmed by the users. And that maybe because we knew that Google Translate uses pivoting via English, as definitely for Ukrainian-Czech, it first translates to English and then to the other language. So we hope that direct translation would be better. And I must admit, I was quite skeptical. I said, well, but this is a real world situation, very serious, and there are the refugees. And if we announce that it's better, but it wouldn't be, then we could cause more harm than good. So we should be really careful. But at the same time, this is like, I was like happy that there is such an initiative and would like to help with it. And we knew that it needs to be done very quickly. So I had also some hopes that this could work in the end, and some experience. So mostly the English-Czech and Czech-English machine translation called Qubit, where we did in 2020 an evaluation, a human evaluation, which was blind, so that the annotators, which included also professional translators and translatologists, didn't know which system is which. But one system was the Qubit translator of ours, and the second was a human reference, which was done by a professional translation agency. And there, in that evaluation, we focus on evaluating separately the adequacy, so how the meaning is preserved, and fluency, so whether the sentences are grammatical, fluent, like style, and neighboring sentences fit nicely with each other, so coherence, and so on. And also it's not on this slide, but we evaluated overall quality. And in this evaluation, the result was that in adequacy, the machine translation was already significantly better than the human translation, while in the fluency it was significantly worse. Actually, here you can see the distribution. The like grades were from 0, the worst, to 10, the best. So there is some distribution. So of course, there are some sentences where the human reference is better also in adequacy, but like in 56% of sentences, the machine translation qubit was better. Then there are some ties. So this was for English-Czech, which is a already high resource language pair. We are collecting the data for decades, the training data, and this is only news translation, which is somehow tricky because it's from many different topics, the news articles, but it's still kind of one genre. And so for the, if you want to know more, then we have a paper where both how the system was developed and the evaluation is described in detail. But now what about the Ukrainian? So it started on March the 1st with the email, and already on March the 12th, we organized a hackathon in the new Impact building in Troja. And the goal of this hackathon in the end was mostly to develop a new front end. We had a front end on Lindat, but we wanted to have also a mobile application and more fancy front end. So there were some volunteers from companies and our friends. And already on like 2 days after that, the first machine translation was published. So meanwhile, during the 2 weeks, we were able, both Jindřich and I, to develop a machine translation system for both directions. And we already had first evaluation done by 2 translators who just took some hundreds of sentences and already saw, or the marks were that it's already better than Google Translate at that time. So we also included some features like here the Ukrainian sentence Zara zavaya hotova is translated to Czech, but here you can see the phonetic transcription so that even people who cannot read it, so the Ukrainian refugees or maybe children who cannot read fluently the Latin script can use the phonetic transcription into Cyrillic, and vice versa. When translating from Czech to Ukrainian, there is a phonetic transcription of the Cyrillic into Latin script. And in April, we improved the quality of the models, and in May, we published an application for Android, done by volunteer Tomáš Krabač. And now, so was it worth the effort? I was still questioning myself. So first, this was meant as a quick solution because we know that the big companies like Google, Microsoft, DeepL, it will take some time before they will improve the model. So it's actually true. We now have checked that the Google Translate, quality of Google Translate has improved a lot since the March. And also DeepL didn't have Ukrainian at all, and it deployed in September. But we had our translation already in March. Also, as I will show on the following slide, there is some advantage in the direct translation, while the other MT systems I know all pivot via English. And we also collected a so-called in-domain test set. So the users who gave us consent to collect their sentences. So we created a test set out of these 10 sentences, which was used later in the WMT share task. So we are not focusing on news translation, although that's also part of the test set because some users wanted to translate, for example, like Ukrainian news to Czech or vice versa, but mostly it's personal communication or some, for example, like school rules and medical like information and so on. So we wanted in general to focus on the needs of the refugees and the people who care about the refugees. So we contacted like tens of humanitarian organizations, first like offering them, we have this system here, and also asking for some training data or feedback. So actually we got almost no training data, except for one translation company, but we got some feedback, yes. And we also offer the translation via API for free if it's for non-commercial purposes. And even if someone needs to use it for some sensitive data, it can be installed on their computer, which is the case of Police of Czech Republic. And one of the biggest users, like the organizations, is Pomáhej Ukrajině, where people can ask for help or offer a help of various kinds. And this message, you can either translate it yourself as a user, but if not, it will get translated automatically via our API. So what is the advantage of direct translation? So for example, in this sentence, the application, let's say, it's ready. The application is here translated as prohlášení, which is correct, I hope, in this context. But when translating via English, it could also be translated as computer application, not as a written form, which is the case of Google Translate and also other translators. Another example, this means I am ill, but due to the ending, it's the feminine adjective. And what about you? And this is the formal the, while here is the masculine and informal. And obviously, here it's, I hope it's the correct translation. Also, we can see here the phonetic transcription is following the Czech pronunciation rules, while, for example, Google uses here the feminine is translated as masculine, and both formal and informal are translated as informal. And also this pronunciation is maybe suitable for English-speaking users, but when translating from Czech, it doesn't really make sense to have the transcription for following English phonetics. So like this, instead of já chorej, would be pronounced ia chvory. And also the medical is translated as narcotics. Yes, I've included also DeepL, so that's correct. Also, like there is a European Union initiative, e-translation. So I've decided to include that there. And Microsoft Bing, actually, I'm not sure if it's an intention, but in this case, it's not showing the gender. So it's kind of clever, even perhaps it's still done via English. So, but in some cases, it's impossible. You need to choose either the masculine or feminine gender. In such cases, Microsoft always chooses the masculine unless there is real, like, obvious that it should be feminine, because, for example, for some pronoun. And maybe even like more unfortunate translations could be when we have a stupid teacher, which is in masculine gender, and the translation durna včitelka is in feminine gender. But if we have clever or smart teacher, then it changes the gender the opposite way. This is the case of Google Translate and DeepL as well. So yes, we can speak about gender bias if it would be from the English translation, where like when not seeing this, you don't know, so you need to guess, and that's a bias. But I would say when translating from Czech, it's a full translation error, not only a bias. Although perhaps it's caused by the bias as well. So just to make sure, yes, Charles Translator, because it's quite easy when we trained on the direct. We did no special effort to make this happen, just training on the direct translation data helps us here. Now about the usage. So this graph shows the thousands of translations per week. So this is the week number from March to September. And one request, translation request, can be a single sentence or 100 sentences. We would need to have another graph, but the general trend is obvious. So while the Czech to Ukrainian usage somehow declines, maybe here people were just interested how it works, or there were some companies who used the API to translate all their web, and then that was done. So the Ukrainian to Czech usage is still growing. Also, thanks to part of this is due to the mobile app. And in September, we organized the Ukrainian-Czech part of the workshop on machine translation share task. And there were 11 systems submitted to this share task, including the big tech companies like Google, Microsoft, unfortunately not DeepL because it was late into the game. It developed it only in September. And these online systems their names are anonymized traditionally in WMT. And it's evaluated again, it's a human evaluation where for each translation, the annotators have to choose a number from 0 to 6 in this case, but it's a continuous scale. And then the scores are somehow normalized, so there are even negative scores. So this is the big picture. Later, I think Jindřich will show you more detailed evaluation. So luckily, we see that the humans are the best according to the human evaluation, although we have some suspicions that the translators we hired didn't translate it fully correctly. Maybe they also use translation via English. We need to look into it further. And there were some systems which got better results than our translation. So for example, we are in contact with the Adam Mickiewicz University, and we already saw that they did much better the job of filtering the training data. And but like all of these systems, at least those which are not high, which are on the wide background, they used only the provided data, which is collected also by us. We provided also some monolingual data to the participants. And for example, here we can see that this online bit, that the Google, it's evaluated as better, but this is already in the, well, I'm not sure when the data was collected, but I think in June or so. So these are the results. And now there will be an introduction to narrow machine translation.
Is this okay? Cool. So hi everyone. So this is going to be an introduction for those of you who have little idea of how NMT actually works. So
go.
So if you already know how NMT works, then you can, go for a coffee, take a nap, go to the restroom, whatever, and be back in like 10 to 15 minutes. So from a very high level point of view, NMT in machine translation, you have a source sentence, here a cat sits on a couch. Then you have some kind of MT model, MT system and or toolkit. And then you expect to get a target sentence, in this case, the Czech translation, na gauči sedí kočka. So let's zoom in a bit. But before we do that, it's worth noting that MT systems do not process sentences as a single unit. They usually split the sentences down to words or tokens. Here the tokens actually correspond to words, but we will see soon after that this is also not the case in present MT systems. But let's for now, let's zoom in into the what the MT here actually does. So it's a probabilistic model in which we have some source sequence of source tokens X, which is here, and we want to generate a sequence of target tokens Y by using this formula, which basically says that take such sentence Y which has the maximum probability given by the source sentence X. And when we say probability of a sentence, we actually mean this, which means give me the sequence which maximizes the chain rule of probability. So we generate it word by word, and in each step we take the probability of that word on that position, given the words which were already generated and also conditioned on the source sentence. So in our models, we don't actually know what these probabilities are, right? So we use a function f, which helps us model the probability distribution. The function has parameters, here denoted by theta. And the input to the function is the source sentence and the prefix which was already generated. But there's a problem with that because X and Y, as we defined it before that, were tokens and not numbers. So we need to do something about this because functions do not operate on strings. So that's why in neural MT, we use so-called word embeddings, which is this large matrix, which has for some vocabulary V, which is a list of every token we consider in the model. It stores a vector of some dimension D, and usually it's like 300 to 255 real numbers. And each word in the sequence is represented here in this matrix, and it corresponds to a vector. So here the word cat is this red vector, and the word couch is this blue one. And we use the word embedding to process the source sequence, and we obtain this list of vectors on the other side. Okay, so now we can express what the model function actually, what are the dimensions of the function. So the input is a matrix of real numbers, which is in the length of the source sentence times the dimension of each of the word embedding vector. And we also have the previously generated tokens represented the same way. So we have additional ty vectors of the same dimension usually as an input to the function. And the output of that function is a probability distribution over the vocabulary V, which we've selected beforehand. One obvious issue with this approach is that the probability in real world is very large. So we need to limit our vocabulary, and we need to still be able to find embeddings and probabilities of words which are not in our vocabulary. So that's why we are using so-called subword segmentation. So if we have a model if we have a vocabulary which doesn't contain these two words, in this case a behemoth cat sits on an antique couch, and we don't know the word behemoth and antique, we can actually split these words down into smaller units, which are called subwords. And we can, in this fashion, we can actually limit our vocabulary down to tens of thousands of tokens, which is feasible to do on a computer. And then you can train the neural network on that on a vocabulary with this size. And then words which are rare or unseen get split to smaller parts. And the words which are frequent in our data can remain as they were. So here it works with subwords. First, we take the source sentence, we tokenize it, and we use subword segmentation to get the sequence of subwords. Then we take the sequence of subwords and we get the embeddings using the embeddings matrix. Here you can see that the cat is here and the couch is here. And these three correspond to the subwords, the representations of the subwords. Then we use our probabilistic model to obtain a sequence of subwords on the target side, which we can then merge to get the target sentence. Na starobylém gauči sedí obrovská kočka. The generation process actually, so here we just assume that we kind of get the output sequence, and on this slide we see the process. How do we obtain this the whole target sequence? So we go word by word, and every time we evaluate this function, we provide it with the embeddings, and then it gives us the probability distribution over the vocabulary, which corresponds to the probabilities of the next word given the prefix. And then we obtain the embeddings of the predicted word and of the whole prefix which was generated. And then we run the function again, and we obtain another probability distribution, and so on and so forth. This algorithm is called greedy decoding because, and in each step, this algorithm gets the highest probable word on the given time step, and it doesn't guarantee that the sentence with the highest probability will actually be decoded, but it's a pretty good approximation. And there are algorithms which are more precise, but there is a trade-off between time efficiency and the translation quality. But there are reasonable approximations such as beam search. So when we have our function f theta, we call the function f the architecture, and the term theta is called the parameters. So most of you already heard about different architectures of neural networks. So in this slang, architecture means our function f. So f is the architecture is given by its structure. In current state-of-the-art systems, mostly we see the transformer architecture, which is illustrated here. I won't go into details of this particular architecture because it's beyond the scope of this seminar. But there were different architectures in the past, namely recurrent or convolutional. But I guess you could also say that phrase-based MT was also an architecture in this sense. And the parameters of our architecture are real numbers. Usually, the neural network architectures have hundreds of millions of parameters, which are all represented as floats, as real numbers. And the values of these parameters are estimated from data using backpropagation. So we start by randomly initializing all of the parameters by some numbers between 0 and 1, or between -1 and 1. And then we use training data, and we use backpropagation. So backpropagation means that when we are estimating the parameters from the data, we define a kind of some loss function of the parameters, which is expressed here, which is in case of translation, the loss function is cross entropy of the model distribution versus the one-hot distribution for each word, which in short means that for each position in the sentence, we have one word from the reference sentence, Y, which should receive the 100 probability in this model, but the neural network assigns a random probability, not random, but it assigns a random distribution over the whole vocabulary. So in this case, our loss function just means the cross entropy between this distribution and between this distribution. And if we define it like this, then this function is differentiable with respect to every parameter included in the neural network structure. So then, given some data, we can compute the gradients of this loss function with respect to each parameter, and then we can update the parameters so the loss function will go down. And empirically, we see that if you do it this way, it will improve also the translation quality. If you compare this to modeling a coin toss, you have an unfair coin, and you need to do a number of observations to be able to estimate the one parameter of the unfair coin toss. So I guess if you have like 10 trials with a single unfair coin, you are pretty much confident in what the parameter should be. Like if it's 5 times tails and 5 times heads, it's safe to say that it's a fair coin. If you have a language, however, it's not that simple. So for each of these parameters, which are hundreds of millions of parameters, you need more and more data to tune all of these parameters. So that's why the size of the training data really matters. And so the more data you have, the better translation quality you can get using these kinds of models. And related problem is a noise in the training data, which you will see. Jindra will talk about data cleaning, what we've applied. So if you can, before you train your model, if you can clean the data, it will help you very much with the translation quality. And even if that is not enough, you don't need to use only parallel data. Here you need to have X and Y pairs from reference data. You can use back translation, which is a technique how to employ monolingual data in the translation process. In short, you regard the monolingual data as the data in your target language. Then you use another machine translation model to translate those monolingual data to the source language, and then you have a set of source and target data, and you can use it along with your parallel data. Yeah, that's it from me. And now Jindra will tell you more about the particular details of training of our Ukrainian system.
Oh, hello. Yeah, I think so. All right. You guys left me plenty of time to talk about how our systems look like. So I will start with the data that we use for our systems. We mostly use publicly available data, and unlike the systems we are used to build for Czech and English and Czech and German, for instance, we could not rely on what EU can provide us because Ukraine is not an EU member. So the biggest sources of data were crawled data from the internet, which were paired using some automatic methods. And those data are very noisy, which is the source of many problems. The second, with a large gap, the second biggest source were the subtitles, and there were also some other minor sources like titles from Wikipedia articles, some IT manuals, and so on. In the first version of our systems, we also used a corpus called Intercorp that was provided by the Faculty of Arts. Later, we found out that it doesn't help much. It couldn't be used in a competition because it's not publicly available, and also it prohibits the commercial use of the developed systems. So in future, we will probably avoid using that. And we did only very simple data filtering. From the preliminary experiments we did, it seemed to be enough, but then later in the competition, we realized that well, our approach to data filtering caused that we were not the best system in the competitions, as you might have already seen on the preliminary results. And what we did was just that we detected the language. One of the most frequent problems was that plenty of the crawled data were in fact in Russian and not in Ukrainian. We checked for reasonable length of the sentences, and we used rules that I will show later, which Martin spent an entire weekend writing regular expressions, but it still was not enough. Oh, that's the other arrow. There are also some other sources that might be potentially used. One of them are scanned books by the National Library, but the problem with that was that it was OCR using a Russian model. So characters which are specific for the Ukrainian alphabet were not recognized well. There might be also some problems with language model, and it's not easy to align them with Czech translation. So this is a potential valuable source, but it was not included in our systems. And of course, we use plenty of monolingual data for back translation, which is sort of a horsepower of today's neural machine translation. We used approximately 7 times more monolingual data than we had parallel data. For Czech, it was quite easy. We used what's already prepared in the Czech corpus, which folks from ÚFAL work on for decades, perhaps at least 1 decade. And for the Ukrainian, we have to look for some data. And the best source that we were able to find is called the Uber text corpus, which is sort of an analogy of the Czech national corpus. The problem was that it was distributed, tokenized, and with removed punctuation. So we had to train models that sort of reversed the process. We took the remaining data that we had, tokenized them, removed the tokenization, and trained a sequence-to-sequence model that reversed the process. And we also just mildly filtered the data again for language identity and also some weird stuff like malformed UTF and other technical things. And what is more important, we also filter the back translation as we do the back translation, because it happens that plenty of the sentences from the monolingual corpora receive totally implausible translations, which we can easily recognize, like it can be like 10 times longer than the source sentence or something like that. So we filter those out as well. And we also played further with the data pre-processing, and we experimented with Romanization of the Ukrainian data. The idea behind that is that Czech and Ukrainian are obviously similar related languages, and there is some lexical overlap between the languages, but even the words which are the same, or the subwords which are the same, don't get the same IDs in the model because it uses different alphabets. So we hope that if we transcribe the Ukrainian Cyrillics into Latin that is as similar as possible to how we write Czech, we can get some improvement. In the end, the improvement was very small and probably not significant in the human evaluation. Anyway, the other requirement for our romanization is that it must be reversible. So if we, for instance, what we do in the web application that we show the transcription, which is like the approximation of how we should pronounce that. This is not usable in this case because it's not reversible. For instance, when in Ukrainian there is this soft character, we would probably just omit it in Czech or write hard Czech somewhere or something like that. But here we need to keep the soft character because we do the translation in our Latin alphabet, but in the end we need to reverse it to Cyrillics. And also there are some text and Latin alphabets in Ukrainian, typically URLs, email addresses, and so on. So we need to find them first, and we add special tags that inform the model that this should stay in the Latin alphabet. And this is this illustrates the biggest problem that we had from the very beginning with the translation model, and this is that named entities, especially city names and also person names, get translated incorrectly. Here we see that in nominative, Jihlava and Kladno, they get translated all right, but when we are supposed to do some declination, vítejte v Jihlavě a Kladně, suddenly Hlava turns into Juria and Kladno turns into Pozitivno, which is not really bad translation, but not the type of translation you would want from such a system. That's a good point. But even if you wrote it separately, you would get the same. It was just a safe space. And the reason for this weird behavior of the system is as in the training data, and especially from the noisy Perl data which were created by matching various sentences from the internet or even from Wikipedia. And those sentences are typically scored with some multilingual transformer-based models, and especially for languages for which the models don't have much resources, they just tend to ignore the named entities. So sentences which were similar but contained different named entities, they were just matched together. This was especially terrible with sentences from Wikipedia because I'm not sure if this is true, but my impression was that especially in sport articles, there were some templated sentences, probably originally in English, which looked like after a successful season 2013, this player transferred to Olomouc or something like that. And from the English Wikipedia, those get independently translated into Ukrainian and Czech, and then by doing this matching, those got aligned together, and suddenly we had parallel sentences which differed differed just in the name of the player or just in the name of a sports club, which lead to this tragically bad translation of named entities. And this error was in the first release of our model, so it was there for a month, and in a shape that, like, with the exception of Prague, all the Czech cities were translated as Ukrainian cities, and vice versa, which is very unpleasant regarding the use that we intended with the translator. So for the second version, we came with filtering using regular expressions. This is the script. Well, this is a snippet from the script that Martin spent the entire weekend of writing the regular expressions for that. And we used that to filter out those sentences where the named entities were wrong. This improved the translation a lot. The problem is that by filtering those sentences, we filtered virtually all the sentences with the named entities. So there are no sentences with named entities left, almost. So the translation of the named entities is still bad. So we came also with a second fix, which is that we try to correct the sentences that we filtered out. We used neural word alignment for that, and we exploit the property that caused the wrong matching in the first place, that the models don't care about the named entities. So if we do the word alignment with them, they are very happy to align the named entities the same way as it was wrong during the filtering or during the matching. And then we replaced the text on the Ukrainian side with just transliterated Czech, which is probably a wrong declination and so on, but hopefully still better than not having the named entities in the training data at all. So we have a code for that. We didn't test it yet, so hopefully in the next version we will be better with the named entities. It was all about data. For the WMT competition, where ÚFAL prepared the test data. We had in the end 2 submissions. One submission was done by Martin. The second submission was done by me and Indra. And there are some minor technical differences. Like Martin used different toolkit. It was tensor to tensor. We used Marian. Martin used a slightly bigger model on the encoder side. Martin uses his block back translation that he talked about. In the beginning, we use something that's called tagged back translation, which is more mainstream in the machine translation community. It just means that at training time, we add a special tag to every back translated sentence, so the model knows, oh, this is the back translated sentence. There might be some errors, so it's distinguished from the hopefully clean authentic data. We both did Romanization. Martin also included something that he calls inline casing. He will talk about it probably later. We use different tokenizers, and there are plenty of minor differences in the hyperparameters that we probably ourselves don't even remember what the different design choices were. And these are the more detailed results from the WMT competition. The first 3 columns show the human evaluation. I never understood how these ranks are computed, but but those ranks say that our systems ended up approximately on similar places. This is, I guess, the most official metric, these normalized human scores. And yeah, this is Martin's submission, which now became what is deployed in a web application. This is, which is slightly better than the online system that we talked about a lot. And in the opposite direction, the results are slightly shuffled. What was done online as Charles Translators, and it was slightly better. Me and Linda was just behind it, and Martin was slightly worse. But we can see that those systems were consistently better than ours. And when we looked at the system descriptions, which are now already available, basically the only thing that they did better was the data filtering at the very beginning. Actually, when they started the back translation, which is iterated, and in each iteration it improved the translation, their systems before they started the iterations were probably already better than what we get after 3 iterations of back translation. So hopefully, if we are able to adapt their filtering methods and add the fixes for the named entities, we can get even a better translation. In the end, I have a few more minutes to tell you a story how evil Martin is. This table, well, he was showing the table at the client conference as well, and at a talk before that was about the European e-translation project, and when he okay. But during the presentation, he quickly measured how bad the e-translation system is compared to ours, and quickly added it to the presentation, so everyone at the event could see how good we are in compared to e-translation. So that's it from us. You can try Martin's Czech English translation and the Czech-Ukrainian translation online on these addresses, and that's all. Thank you for your attention.